3.6 Marginals and Differentials. Southwestern College, Professor Maria Olivas. This section is on section 3.6 Marginals and Differentials. We are going to be learning about how to find marginal cost, revenue, and profit, find delta y and delta dy, and use differentials for approximations. All right, let's go ahead and start here by drawing a picture. Okay, so my picture here, it's just to help give you an idea of what I'm going to write up ahead here for our marginal cost definition. Let's let one of our axes here represent C of X, which is going to represent our cost in dollars. And that's going to represent like our y-axis. And let's let this other axis here, the x-axis, we're just going to call it X, represent the number of items. So I'm going to go ahead and draw just a graph here of a function, just representing any general function here. I'm just going to call this function here, we're going to call it C of X. I'm going to go ahead and plot a couple points on this graph of this function. So why don't we go ahead and this point right here, I'm going to label this with an X value of, why don't we just call it, let's be real creative. Let's call it X. Yeah, I like that. And let's call the Y value, let's be real creative with this one too. How about we call it C of X? And then we're going to come up with another point right here. And we're going to say that this is just going to be 1 unit more than X. So I'm going to call it X plus 1. And therefore, the Y value associated with this X coordinate for this ordered pair, this is going to be C of X plus 1. Okay, so I think you can clearly tell here by looking at our picture, looking at our graph that we have drawn, that there is 1 unit of difference between the X and the X plus 1. So if I were to add 1 unit to this X, that gives me the X plus 1. So this is, if I were to subtract them, right, X plus 1 take away X, that would also just give me a unit of 1. So it's 1 unit of distance separating those two X coordinates. This rise for this slope triangle here that I kind of drew right here, this is going to be represented by C of X plus 1 minus C of X, right? If you subtract the Y values, that's going to give you the rise. Why don't we call that something else instead of me writing that whole long thing right there? Or no, I'm gonna just leave it like that. Let's just leave it as that. So we can tell here I'm connecting these 2 points right here so that you can clearly tell that what I'm trying to get you to see here is kind of like this represents like a slope triangle right here. And you can, and if I were to extend it, I would get the secant line. So then you could easily figure out what the slope of that secant line is. It would just be C of X plus 1 minus C of X over 1, right? Rise over run. But let's pretend I said here, you know what? I'm going to get the tangent line at this, I'm really bad here at drawing tangent lines. I'm going to try my best here. I want to get the tangent line at X, right here. So C prime of X right here, and it's tangent right at that X value. Now C prime of x is going to be approximately equal to that C of x plus 1 minus C of x. Because if you look at the little triangle that I can make here from that tangent line, it's almost the same, right? It's really close. You guys can tell by looking at this height here that I'm representing with this C prime of x and comparing it to the C of x plus 1 minus C of x, that those vertical values are really close. So that C prime of x, that's what I'm going to call basically our marginal cost. The marginal cost at x given by C prime of x is the approximate cost of the x plus first item. So that is I just want to emphasize here approximate. That's why I put an approximately equal to sign over here. And I'm going to represent this with C prime of x is approximately equal to C of x plus 1 minus C of x. If I wanted the exact value for this, another way I could call this delta C of x. It's another way that we can call the exact value or the exact change there. So we call that delta C of x. And that represents the actual, or another word, exact, the exact change in cost. So another thing that I can do right here is I could rewrite this. If I wanted to rewrite this, I could add C of x to both sides here. Right? And then you'd see how the C of x would cancel out. I'm going to write the C of x plus 1 first. So I'm going to move that C of x plus 1. Write that first in the front. So I'm just going to make everything just switch sides. C of x plus 1 is going to go first. And that's still going to be is approximately equal to C of x plus C prime of x. So it still basically means the same thing. I just rewrote it a little bit. So once again, this is the approximate cost of that x plus first item. Or another way to think about it, you can think of it like instead of thinking of marginal cost as a derivative of cost, it can roughly be interpreted as the cost of producing an additional unit, if that makes it easier to understand. The marginal revenue at x given by r prime of x is the approximate revenue for the x plus first item. That is, r prime of x is going to be approximately equal to r of x plus 1 minus r of x. Now this, if I wanted to call this like an exact amount, another way to refer to this as the exact amount, I could refer to this as delta r of x. And once again, that just represents the exact change in revenue. And then r of x plus 1 is approximately equal to r of x plus r prime of x. And that's doing exactly what we did above with the marginal cost. I can add to both sides r of x and then just switch everything around, and it just gives me another statement that I can write down that I can use to help me understand this. The marginal profit at x given by p prime of x is the approximate profit from the x plus first item. That is, p prime of x is approximately equal to p of x plus 1 minus p of x. And this is going to be equal to delta p of x, which means the exact change in profit. And p of x plus 1 is approximately equal to p of x plus p prime of x. All right, so that's just very similar to what we've already written down for marginal cost and marginal revenue, marginal profit as well there. Also, since p of x Remember that we could write the profit function, same thing as R of X minus C of X, right? You can subtract the cost function from the revenue function, and that's going to give you the profit function, P of X. And P prime of X is also going to be equal to R prime of X minus C prime of X, right? Or the derivative of the profit function is equal to the derivative of the revenue function minus the derivative of the cost function. So the first one represents our profit function. The second one represents our marginal profit function, or the derivative of our profit function. All right, I think we're ready for our example number 1. Let's go ahead and go on to example 1. Given C of X is equal to 50x squared plus 25,000, and R of X is equal to x cubed minus 10x squared plus 50x plus 20, find the total profit. Well, P of X, our profit function, is just going to be equal to R of X minus C of X. So all I have to do is subtract these two functions that were given to me up above. I do have to be careful about the order. R of X has to go first because R of X represents the revenue. Remember what revenue means. Revenue is the income generated from sale of goods or services before any costs or expenses have been deducted. And what we're doing here is we're subtracting the costs from the revenue in order to find the profit, right? So cost is what the business spends to produce the goods, right? Okay, so let's begin by writing P of X. P of X is going to be equal to our R of X function, which is going to be x raised to the third power minus 10x squared plus 50x plus 20, and that's all within a set of parentheses to represent R of X. And we're going to subtract from that, open up a set of parentheses, 50x squared plus 25,000, and then close the parentheses, and that's going to represent our C of X. I'm going to distribute that minus sign. So if we distribute that minus sign here, we're going to end up with P of X equals, the R of X function is going to stay the same there, so I'm just going to recopy it, x cubed minus 10x squared plus 50x plus 20, and here we're going to change the sign, so we'll have minus 50x squared minus 25,000. Now I look for like terms that I can combine. So P of X is going to be equal to x raised to the third power minus 60x squared plus 50x minus 24,980. This is going to represent P of X, my profit function. So I'm going to go ahead and box that in. Part B is total cost, revenue, and profit from the production and sale of 60 and 80 units of the product. So we are basically looking for 6 different answers. So I'm going to circle the 60 and the 80 to represent the production and sale of 60 and 80 units of the product. And then we're finding total cost, revenue, and profit for each of those numbers. So 6 answers, and I wrote down 6 answers next to there. Let's start off with the first one. I'm going to call this number 1, x equal to 60. Let's go ahead and substitute x equal to 60 into our cost function. C of 60 equals 50 times 60 raised to the second power plus 25,000. This is going to be equal to $205,000. R of 60 Now we're plugging into the revenue function. I'm putting clouds around the functions that we're using, and then I'm drawing arrows pointing down to where I'm doing the work. So now I've drawn a cloud around the C of X, and I've drawn an arrow pointing down to the C of 60 part, and I've drawn a cloud around the R of X, and I've drawn an arrow pointing down to the R of 60 part. So R of 60 is equal to 60 raised to the third power minus 10 times 60 squared plus 50 times 60 plus 20 equals $183,020. Next, we're going to find P of 60. I'm going to put a cloud around the function that I just found in part A, P of X, and I'm going to draw an arrow pointing down to P of 60 so you know which function I'm plugging into. So P of 60 is going to be equal to 60 raised to the third power minus 60 times 60 squared plus 50 times 60 minus 24,980. This is going to be equal to negative $21,980. So a negative profit. Another way to find P of 60 would be to find R of 60 minus C of 60. So if I just input the values I got for R of 60 and then subtract C of 60 from that value, I should be able to get the same answer. So let's see, we get here that this equals $183,020 minus $205,000, and this is equal to negative $21,980. So yes, it checks out. So that way I feel good about my answers. And I have drawn an arrow pointing from our P of 60 that I did earlier from the P of 60 I did right now, and I wrote the word same. That way I know it's the same answer, and I've boxed in all my answers for C of 60, R of 60, and P of 60. Number 2, now we're going to check for X equal to 80. So I'm going to have C of 80 equals 50 times 80 squared plus 25,000. This is going to be equal to $345,000. R of 80 is going to be equal to 80 raised to the third power minus 10 times 80 squared plus 50 times 80 plus 20. And this is going to be equal to $452,020. P of 80 is going to be equal to 80 raised to the third power minus 60 times 80 squared plus 50 times 80 minus 24,980. This is going to be equal to $107,020. And if I wanted to do this the other way, my P of 80, I could find R of 80 and subtract C of 80 from that, and this would be equal to $452,020 minus $345,000, which would be equal to $107,020. And they're the same. The answer that I got for P of 80 that I just did right now beforehand, it's the same as the P of 80 that I did right now. And I have boxed in all my answers for C of 80, R of 80, and P of 80. C. The marginal cost, revenue, and profit when 60 units are produced and sold. Also determine these values when 80 units are produced and sold. Interpret your results. So let's go ahead and find that. In order to find marginal cost, marginal revenue, and marginal profit, I'm going to have to find the derivative of each one of those functions. So first, let's start off by writing C of X. C of X is going to be equal to 50x squared plus 25,000. So now I need to find C prime of X, the derivative of C of X. So C prime of X is equal to 50 times 2 is going to give me 100x plus 0, since the derivative of a constant is 0, so it's just going to be 100x. I'm going to draw a vertical line segment here separating the work that I'm doing here for C of X and C prime of X from R of X and R prime of X. So to the right of the vertical line segment, I'm going to write R of X is equal to x cubed minus 10x squared plus 50x plus 20. R prime of x is going to be equal to 3x squared minus 20x plus 50. So that's my marginal revenue function. Now I need to find my marginal profit function. So I'm going to go ahead and shrink the work that I've done here a little bit towards the left-hand side so I have more space on the right. I drew a vertical line segment to separate the work from the R of x and the R prime of x from the P of x and the P prime of x. On the right-hand side of the vertical line segment, I'm going to write P of x. P of x equals x cubed minus 60x squared plus 50x minus 24,980. P prime of x is going to be equal to 3x squared minus 120x plus 50. Now that I have all of my functions that I need to do this problem, by the way, I'm going to shrink the P of x and the P prime of x just a little bit so it matches the size of my C of x and my R of x functions. Now that I've found my three functions that I need here, I'm ready to do some substituting, some evaluating of functions. I've drawn a horizontal line segment going across the screen here to separate the functions that I just found from the work that I'm going to do in evaluating these functions. Let's start off by evaluating C prime of x. So I'm going to write marginal cost because that is the marginal cost function, and then after that, after the words marginal cost, I'm going to copy down C prime of x is equal to 100x. C prime of 60 is going to be equal to 100 times 60, which is equal to 6,000. And I'm going to write this as $6,000 per item. Next, I'm going to write C prime of 80. This is going to be equal to 100 times 80, which is equal to $8,000 per item. I've underlined the words marginal cost. I'm drawing a horizontal line segment going across the screen to separate the work I did right now for marginal cost. And underneath that horizontal line segment, I'm writing down the words marginal revenue. I'm underlining those words. And to the right-hand side of these words, I'm going to write down the marginal revenue function, which is going to be R prime of x is equal to 3x squared minus 20x plus 50. Now we're going to evaluate this function. We're going to start off by evaluating it at x equal to 60. So I'm going to go ahead and write here to the right, R prime of 60 is going to be equal to, actually I'm going to just do this in the calculator and I'm just going to go ahead and write the answer here. So R prime of 60 is equal to $9,650 per item. And R prime of 80 is going to be equal to $17,650 per item. I'm going to draw a horizontal line segment going across the page, or across the screen. Underneath that horizontal line segment, I'm going to write marginal profit and underline those words. And then to the right of where I wrote marginal profit, I'm going to write P prime of x is equal to 3x squared minus 120x plus 50. To the right of that function, I'm going to write P prime of 60 is equal to, and I'm just going to go ahead and do this in the calculator, and I'm going to get the answer $3,650 per item. And for P prime of 80, I'm going to get this equals $9,650 per item. So C prime of 60, R prime of 60, and P prime of 60 are approximations for C, R, and P of the 61st item. C prime of 80, R prime of 80, and P prime of 80 are approximations for C, R, and P of the 81st item. I've gone ahead and I've boxed in the answer that I just wrote down. Be sure you understand the difference between marginal cost, revenue, and profit versus average cost, revenue, and profit, as discussed previously. The average cost per unit for 60 units is average cost is going to be equal to C of X divided by X. So X is going to represent the number of items, the number of total items, and the C of X is going to represent the cost, right, of that number of items, the total cost. So if you divide the total cost by the number of items, that should get you the average cost per item. So C of 60 divided by 60, in this case, it would give us $205,000 divided by 60, because we have 60 items. And then that average would come out to $3,416.67 per unit, or per item, right? We could also use the word item. Either one is fine. But this is an average cost. Section 2, differentials. Okay, we're going to draw a diagram here, or a sketch of a graph. I'm going to go ahead and draw a coordinate plane. So I'm going to start off by drawing the vertical y-axis. Then I'm going to draw a horizontal x-axis. And this coordinate plane, we're focused primarily more in quadrant 1. You can see a little bit of quadrant 2, 3, and 4, but just a little bit. It's more of the focus is in quadrant 1. I'm going to go ahead and draw a function on here. I'm going to just draw a curve. This curve is going to be increasing and concave down. And I'm going to go ahead and label this curve as y. And I'm going to call it y equals f of x. I'm going to go ahead and choose 2 points on here. This first point, let's call this x-coordinate x, because I'm feeling really creative. And I'm going to call this y value, yeah, you guessed it, f of x, yes. And I'm going to go ahead and choose a second point that's on this function. And this time, instead of using where I went up by just 1 unit, I know that's what I was doing when we were working with the marginal cost, and I said we're going to go up by 1 unit. I'm going to go up by, let's just call it a really small amount. Let's call it delta x. And let's just say it's a small amount that I'm going up by, and I'm not going to specify that amount. The amount separating x and x plus delta x is delta x, and it's a small amount. And that's good enough for us. And I'm going to do the same thing over here. The y value for this point right here, the y coordinate, we're going to call this f of x plus delta x. So now we got to figure out, well, what's going to be this difference between f of x plus delta x and f of x? Well, remember what we did before, we subtracted them. But what I'm going to do for now is I think I'm going to call this, because that'd be a long, thing to write down. What I'm going to call is delta y. Delta y, that little delta, the triangle just means basically the change. So this delta y is like the change in y value. But you know what? I'm going to write down what this actually means, right? The change in y's is basically just the difference in y's. So delta y is going to be equal to f of x plus delta x minus f of x. That's what delta y is equal to. It's the change in y's, right? Or the difference in y. Okay, now let's go ahead and do our rise over our run. So I'm going to draw what looks like a little slope triangle here. This is going to represent delta x. This is going to represent delta y. Our rise over our run. This should remind you a lot of slope. Delta y over delta x. The change in y's over the change in x's. So here, at this point, I'm going to draw a tangent line at x. And then I'm going to draw this point that's going like, I'm going to draw another slope triangle, but this time it's going to be connected to the tangent line at x. And I'm going to call this dx for the run, and instead of delta y, I'm going to call this dy for the rise. This dy, we like to call that the differential. Notice that delta x and dx are equal to each other. That measurement is still the same for both. So I'm going to write dx equals, right? And we know the difference between equals and approximately, right? Equals means it's exactly equal to this. Dx is exactly equal to delta x. They're exactly the same amount. They're always equal to each other. Now dy, now that's not exactly equal to delta y. So I'm going to write it's approximately equal to delta y. Kind of remember like we were working with the marginals, right? And we said that the derivative of the cost or the marginal cost was approximately equal to. And here I'm going to write that delta y is exactly equal to the change in y's, or f of x plus delta x minus f of x. Our delta y represents the true change in y, or in other words, the exact change, right? We use an equal sign when we're talking about exact values. So it's the exact change in y. That's why we're allowed to use the equal sign there when I represent something with the delta y. Okay, so I think we're ready to go on to our next example. Example 2. Consider the function f of x is equal to 9 times the cube root of x. Find dy when x is equal to 64 and dx is equal to 2. Maybe before I do this problem, I should kind of set it up and draw a picture and kind of explain like why we're doing everything we're doing here so it makes a little bit more sense. Okay, so let's go ahead and do that. I'm going to draw a picture right over here on the side. You might want to go ahead and just plug this function into your calculator. I'm just going to draw a sketch of it. It doesn't have to be perfect. It's just so you get a sense of the picture of it. You guys can put that into your calculator. This isn't what it's asking for. It's not asking you to draw a graph. I'm doing it to help bring some understanding, and I'm trying to shed some light. So here's our function. F of x is equal to 9 cube roots of x. It's asking for dy when x is equal to 64 and dx is equal to 2. So why don't we go ahead and label this point here where x is equal to 64. And let's go ahead and label the y value. Well, let me first write this down. 64 plus 2, the dx would be 66. So that would give me that second point that we were talking about earlier in that picture I drew. And now let's go ahead and write down the y value that's associated with this ordered pair, the y coordinate. In order to find the y coordinate, I need to substitute 64 in for f of x. Value right here, 9 times 4, which is 36. So this y value is equal to 36. So that's this point here. So this is what this is used for. Differentials oftentimes are used to help us approximate values. So if I were to draw this tangent line here, it's tangent at x equal to 64, I could use that tangent line to get that dy value, to get a pretty close approximation to help me approximate what would be the value when x is equal to 66. Now I know what you're thinking. See, I could just plug that into the calculator. Well, let's pretend you couldn't. Let's pretend you're on a deserted island and you don't have a calculator, and you need to figure this out. That's basically why we're doing this. We're trying to say, how could we figure this out? Get a pretty close approximation, to this if we didn't have a calculator, back in the old days type of thing. All right, so dy, we're looking for what the dy is here. So basically here, f of 64, we already know that f of 64 is equal to 36. But we don't know what f of 66 is because we're going to pretend we don't have a calculator, right? And this is what it's leading up to. So look at part C. Use the result from part A to estimate 9 cube roots of 66. So we're basically trying to say, how could we use something like, if we do know the value of x is equal to 64 without a calculator, how could we use that to try to get a value that we wouldn't know, like without a calculator, right? So what I'm going to do here, first, I'm going to write down my function. I'm going to write it with a y. And then I'm going to write dy dx is equal to, I'm going to take the derivative, 1/3 times 9x raised to the 1/3 minus 3/3. So it looks like here dy dx is going to be equal to, I don't have enough space. Let's make this a little bit smaller so I've got a little bit more space here to work with. Good. Dy dx is going to be equal to 1/3 times 9 is just going to give me 9/3, and 9 divided by 3 is just a 3. And then that's going to be x raised to the negative 2/3 power. So this is my derivative. This is my derivative of y. Now I'm going to rewrite this. I'm going to move that dx over to the other side. So instead of this is going to give me dy is equal to 3x raised to the negative 2/3 dx. Now this represents the differential of y. This is dy. Now in order for me to find dy, I need to substitute everything I know. I'm going to substitute 64 is equal to x, right? Or x is equal to 64. So 3 times 64 raised to the negative 2/3 power. And then I'm going to do times dx. But dx is just a 2. Now we just figure this out. Dy is going to be equal to 3/8, which is also exactly equal to, this is an exact decimal value, 0.375 or 375 thousandths. So because it's an exact value, I can put an equal sign there. Okay. That gives me that dy, that differential that I was looking for. Next, part B, find delta y as x changes from 64 to 66. Compare the dy value from part A. Delta y is equal to, remember we said this already, f of x plus delta x minus f of x. The delta x is equal to the dx. Do you guys remember we wrote that earlier, right? So I'm going to write down a 2 for delta x. So remember, they told us dx, this distance between 64 and 66, this is dx, and that's equal to 2. And dx is exactly equal to delta x. So we can substitute 2 for delta x. So this is going to be delta y is going to be equal to f of 66. You know what, let me rewrite this so it looks a little, I like to show every little step. F of 66 minus f of 64. And now we'll do the actual substitution into the function. Delta y is going to be equal to 9 times the cube root of 66 minus 9 times the cube root of 64. Okay, now we can use our calculator for this part right here. Okay, so we're going to use our calculator right here. So we're going to pretend we have our calculator back, and we're going to get an approximation. Our approximation comes out to 0.371. Now look at this approximation for delta y. Isn't this really close to our dy, our differential? I know what you're thinking. You're thinking, yeah, these are really close. It's amazing. They're amazingly close. So yeah, this is what usually happens. So our differential value will usually be very close to that exact value. This is why we can use this to help us make approximations, especially like, in the old days when people didn't have calculators. This is very easy to do problems that were like impossible to do without a calculator. But like for our purposes, like I said, let's just kind of pretend we're on a deserted island and we don't have a calculator, and the islanders want you to figure this, approximation out. And they're like, please figure this out for us. And you're like, okay, So 9 cubed roots of 66 is approximately equal to 9 cubed roots of 64 plus dy. So 9 cubed roots of 64 plus 3.375, which is 36 plus 0.375, which is equal to 36.375. So this is what the result comes from part A. If we use that result to estimate our 9 cubed roots of 66, that's what it comes out to. That's the approximation.